Hi, this is Mrs. Young, and this is our first lesson in our unit on circles. So a lot of times when you start a new unit, you have a lot of new terminology. So we're going to start with a little bit of vocabulary here. The first two, interior of a circle and exterior of a circle, you don't necessarily have to write down unless you'd rather. Obviously, the interior of a circle refers to all of the points that are inside the circle. An exterior of a circle is all the points outside the circle. So I just want to make you aware of those two first. The ones that you should write down for me, we have chord, secant, tangent, and point of tangency. So I'd like you to take a minute, pause the video, and write down these four vocab words, their definitions in the picture. So again, pause the video, copy down the four vocab words. So the chord is a segment whose endpoints lie on a circle. So as my example in my picture, AB, that's a chord. A secant is a line that intersects a circle at 2 points. So we have this blue line. Notice the arrows on the end show that it keeps going. So a secant goes on forever in both directions. That's line L. And then a tangent is a line in the same plane as a circle that intersects it at exactly 1 point. So this line M down here, again, a line extends forever, touches the circle at exactly 1 point. So that is a tangent. This point of intersection where the tangent line intersects the circle is called your point of tangency. So point C is my point of tangency. Notice that, again, a chord is a segment. It has distinct endpoints, right? So this is a chord. A secant goes on forever. It's a line that extends forever in both directions. But both of them will hit a circle in 2 points. So technically, there is a chord contained inside a secant, right? So that piece of the secant that's inside the circle, that's a chord. A special type of chord that goes through the diameter is called, that goes through the center of the circle is called a diameter. So those are some of our new terms, and I thought I'd have you practice a few of those. Well, maybe we'll do this together. So to identify each line or segment that intersects circle L. So we have this circle L. What are the chords? I see two chords here. I see a chord JM and then a chord KM. Those are both chords because the endpoints lie on the circle. Again, just that piece or section, that segment. A secant, I only see one secant in my picture. That's this line JM that goes on forever in both directions. So that's my secant. Notice the difference in the notation between the chords and the secants, right? So JM is the line, JM as a secant is a chord, JM as a line is a secant. So notice the difference there. Tangent, I only see one line that's tangent, that's line M. Diameter, hopefully you recognize there's only one diameter, KM. And then again, notice that KM is both a chord and a diameter. So a diameter is a special or specific type of chord. Radii, what radii do you see in the picture? I see 3 radii. I see LK, LJ, and LM. All 3 of those are radii. They go from the center to the edge of the circle. So again, make sure that you're familiar with all of these terms and their representation in circles. Next, we have a couple of other definitions and theorems to write down. So this first part, we're going to be writing down some things. So go ahead and pause the video here and write down these 3 terms: congruent circles, concentric circles, and tangent circles. Write down their definitions and their pictures. So go ahead and pause the video and write these down. So congruent circles have congruent radii. So they're exactly the same size and shape. Concentric circles are coplanar circles, meaning they lie in the same plane or flat surface and they have the same center. I always think of like a bullseye or the Target logo, right? Those are concentric circles. And then tangent circles are, again, coplanar circles. They lie in the same flat planar surface and they intersect at exactly 1 point. So in tangent circles, like here, right, there's a point of tangency, or here's a point of tangency where those 2 circles intersect. So those are called tangent circles. Notice that they can be internally tangent, where one's inside the other, or externally tangent, where they're not one inside the other. Next, we have just a couple more definitions here. Common tangent is a line that is tangent to two circles. So there's common external tangents, right? And then the other example here on the right, these are common internal tangents just because they cross in between the two shapes, whereas the common external tangents just stay on the outside of the circles. So again, we have common tangents. You might want to pause the video and copy these down as well. Next, we have a couple theorems. Here's our first theorem. If you don't want to write down, I know these are kind of wordy, if you don't want to write down all the words, then maybe you can write down the abbreviation down here, which is what you would use if you were using this in a proof. If a line is tangent to a circle, then it's perpendicular to the radius drawn to the point of tangency. So again, if a line is tangent to a circle, this line L is tangent to the circle at that point, there's my point of tangency, right? Then it must be perpendicular to the radius. So we know by this theorem that it's going to be perpendicular to that radius. The second theorem is really just the flip or converse of this. If a line is perpendicular to a radius of a circle at a point on the circle, then the line is tangent to the circle. So again, if the line's perpendicular to the radius, then it must be a tangent line. Back to the first one, if our line is tangent to the circle, then it's automatically perpendicular to the radius. So again, one is really just the converse of the other. So I'd like you to take a minute to pause the video and go ahead and copy these down with your pictures as well. And then finally, our last theorem for today. If two segments are tangent to a circle from the same external point, then the segments are congruent. So again, if two segments, remember we have lines that are tangent, but here we just want to look at a segment that is tangent. So if it's tangent to a circle from the same external point, that's point A, then the segments are congruent, which I marked them in the picture. AB and AC are automatically congruent if those two tangent lines intersect at that point A. And we can use this to help us solve some of our problems. So go ahead and pause the video and copy that last theorem down. Okay, so now we're going to go through a few examples applying some of the stuff that we just talked about. And some of these are check it out right directly from your packet. So if you want to look at your packet as well, you can. Number 2, find the length of each radius, identify the point of tangency, and write the equation of the tangent line at this point. So again, the first thing it says to do is find the length of each radius. So for, let's say the radius of circle D, again, I'm just going to count. It's 1, 2, 3 squares long, right? So this radius right here, that's 3. So the radius of circle D is 3. If I look down here at circle C, again, this is really easy in the coordinate plane. We're just counting the squares. So the radius of circle C is just 1 unit or 1 square. It says identify the point of tangency. So I can see in my picture that the two lines intersect right here, right? That's that point of tangency between the two circles. So I can say that my point of tangency is, let's see, the right 2 down 1, so it's 2, -1. And then the other thing that they want is the equation of this tangent line. So they even drew it in for you, right? They drew in that tangent line for you. What's the equation of that line? So the equation of your tangent line, think back to, I'm sure Mrs. Hoekstra taught this in algebra, but I think I've mentioned it too. I always try to use my mnemonic device to help me remember my special cases, my horizontal and vertical lines. I remember if it's a horizontal line, it's going to have a 0 slope, and the equation's in the form y equals some number. So that horizontal line, the equation will be y equals, and again, you're just going down 1 on the y-axis, so it's y equals -1. Every point on that line has a y-coordinate of -1. Nice. Gosh, that's pretty easy, right? Let's try another sample problem or practice problem. Again, this is another check it out from our packet. This is check it out 4. I remember that if the lines are tangent, RS and RT are tangent to the circle, then they must be congruent to each other. So we can use that last theorem that we wrote down to help us solve for our x value. And then once we find x, then we can use that to solve for RS. So this one here on the left, we can say x over 4 equals x minus 6.3. I'm trying to solve this for x. For me, normally I like to get rid of my fractions first. So I'm going to multiply both sides of that equation by 4. Multiply the left side and right side by 4. That's just going to help me get rid of that fraction. So x is equal to 4x minus, I think that's 25.2, I think. Yes. And then I can go ahead and subtract 4x from both sides. So 1x minus 4x is negative 3x. And then I can go ahead and divide both sides by negative 3. So I came up with x is equal to 8.4. Am I done? No, because I'm trying to solve for RS. So I could just take 8.4 and divide it by 4, right? RS, 8.4 divided by 4, and I came up with 2.1. So RS is equal to 2.1. So there's my answer for that one. For the one on the right, again, similarly, if RS and RT are tangent, then they are congruent. So I can say that n plus 3 is equal to 2n minus 1. It's a pretty easy one to solve. I can subtract n from both sides and add the 1 over to the left side. So I just got n is equal to 4. Remember that we're trying to solve for RS, so I can take the 4 and plug it back in, and I can say 4 plus 3, I'm going to get 7 for my length of RS. So RS is 7. So applying that last theorem in a few practice problems. Finally, one more practice problem from the packet. Okay, so this is another good practice problem. If you want to follow along with me, this example that I'm going to look at first and talk about is actually on page 4 of your packet. And it's applying the other theorem that we wrote down in our notes. It says here the summit of Mount Everest is approximately 29,000 feet above sea level. What's the distance from the summit to the horizon to the nearest mile? One thing that hopefully you notice also there in the left-hand margin of page 4, some important helpful hints. First of all, remember that 5280 feet is equal to a mile, and also that the Earth's radius is about approximately 4,000 miles. We're going to be using that in our problem. One thing that maybe you noticed right away is that they gave us something in feet, but they want the answer to the nearest mile. So that's why I know I'm going to have to convert to miles. So that's why they gave us the conversion rate there. So that's what they do first, is they take that 29,000 feet and divide it by 5280 to figure out how many miles that is. Another thing that's going to be helpful that I expect you to do is draw a picture to go along with this. So we are using a circle to represent Earth. And this point up here, E, must mean Everest, right? So we know that Mount Everest is 29,000 feet above sea level. That's this little distance right here. So when you take the 29,000 divided by 5280, we get 5.49 miles. So that means this little piece right there, that mountain is about 5.49 miles tall. They also told us over here in the margin that the Earth's radius is about 4,000 miles. So they did mark that here, right? There's my radius of Earth. It's 4,000 miles. But notice that all the radii are 4,000 miles. So that means even this radius right here, DC, is also 4,000 miles. So when I add those two pieces together, right, if we add 5.49 and 4,000, we get 4,005.49. That represents, and hopefully you're noticing this in the picture, that represents the hypotenuse of this right triangle. This other radii, 4,000, represents one of the legs, and we're just trying to solve for the missing leg. So from Mount Everest to this point on the horizon, that's a point of tangency. And since this is a tangent point, we know it's at a right angle or perpendicular to the radius, which creates a right triangle, which allows us to use Pythagorean theorem to solve it. So you're going to see problems like this in the homework and probably on assessments or whatnot. So make sure that you can draw the picture, know how to convert your units. And then once you apply your Pythagorean theorem here, again, you're just plugging the numbers into your Pythagorean theorem, they got about 2,010 miles. So again, this distance from Mount Everest to this point on the horizon is about 210 miles. So we're going to do a practice problem together just like this. So Kilimanjaro, the tallest mountain in Africa, is 19,340 feet tall. So again, the first thing I would do is draw my circle. Yes, I'm totally cheating. There's my circle. And we have this mountain, Mount Kilimanjaro. It's up here. I'm going to put K for Kilimanjaro, right? This is my mountain. There's my mountain. And somewhere we have the center of Earth, right? And we want to know what's the distance from Kilimanjaro to this point on the horizon. This point out here, this distance is what we're trying to solve for. And since this is our point of tangency, we know that it's perpendicular or at a right angle to the radius. Just like the last problem, we know that Earth has a radius of about 4,000 miles. We have to convert our mountain height. So we want to take this 19,340 and we want to divide it by 5,280. You're going to get a decimal for sure. You want to maybe carry that through on the calculator. I'm just cautioning you, don't round too much, but I think you get something about 3.66. I don't know what it is. I can't remember. Use your calculator. So when I take that and add it to the 4,000 radius, then we know that our hypotenuse is about 4,003.66. Again, I'm trying to carry that number through on my calculator. That's my hypotenuse of my right triangle. So we can say the one leg, 4,000 squared, plus the other leg, I don't know what it is, I'm just going to call it b squared, you can call it b or whatever you want, is equal to your hypotenuse squared. So from here, I'm just going to use my calculator, plug it in, and I came up with about, on my calculator, about 171.22. Double check on your calculator, make sure that you can come up with the same value. Notice that it says to round to the nearest mile. So at the very end, I'll round this to about 171 miles. Again, that's the distance from the peak of Mount Kilimanjaro to this point on the horizon. And you're using your Pythagorean theorem to help you solve it, in addition to converting units. Finally, we're going to have you do just a couple practice problems on your own. The first one says FE and FG are tangent to circle J, find FG. And then the second one, instead of using Mount Kilimanjaro, we're using Mount Mitchell, but the same kind of problem that I just went over with you. So go ahead and pause the video and try to solve these two problems. Okay, so in that first one, I set FE equal to FG. In my first step, I did my distribution there, distributed the two. You could have honestly divided both sides by 2 first, just another way to do it. You should come up with algebraically x is equal to 7. Notice they want you to solve for FG, so I take the 7 and plug it in, and I came up with 90. So your final answer, number 1, is 90. Number 2, again, we're talking about Mount Mitchell. So you take the 6,684 and divide it by 5,280, you get something that's about 1.2659 ... I take that number, that's the height of the mountain, and add it to the radius of Earth, 4,000. That gives me my hypotenuse in my Pythagorean theorem. So I take 4,000 squared plus, you can call it a, b, question mark, x, whatever, squared, is equal to your hypotenuse squared. From there, I'm using my calculator. I came up with 100.6423, so you can go ahead and round that to about 101 miles. So going to make sure that you are comfortable with doing those types of problems, those mountain problems. The only difference is we keep doing them in feet. Sometimes I've seen problems where they do it in metric units. I've also seen problems where sometimes they're on Mars instead of Earth. So just be careful what type of problem you're doing and what the units are. Finally, our homework for tonight is going to be pages 6 and 7 in our new circle packet. You're doing numbers 11 through 27. Again, those packets are posted in excuse me, Google Classroom, as are the stamp sheets. So you want to refer to them. You don't necessarily have to print them out unless you want to, but you can go ahead and refer to them in Google Classroom. So tonight's homework, page 6 and 7, 11 through 27. Do it in your spiral, take pictures, and then make sure you send it to me. Thanks, guys.